All right. So I don't want to take time to read, like just read off answers, whatever the answer books here. A lot of them are odd, so you could look up. So let's talk about ones you had questions about, ones where you're not quite sure you understood. If this was on a quiz tomorrow, which actually our quiz, we'll probably do a quiz on all this stuff that we kind of talked about here recently Monday. So we'll kind of talk more specifically tomorrow about what that is, but pretty much the stuff we've done the last couple of days today. We have one new thing to kind of talk about today. We'll reinforce that more tomorrow. And kind of be talking about it. We'll probably do like we did on the last quiz. We won't do that all the time, but review a little bit before the quiz with a few problems. But and since it's a Monday, that's not a bad idea either. So anyway, that's our next quiz. So anyway, what do you look at? Obviously, some of you said the story problems, maybe 70, 71, 67. Some, that section, but so we can get to some of those. But how about before that? 21 through 29 odd, or 57, 59, 61, any of those?
64.
64?
Yeah.
Okay. Anything before 64? How about that 57, 59, 61 section? Is that easy? Okay. Let's talk about that, because that's good. I mean, I think it can be easy, but we haven't really seen that. And here's the thing to keep in mind. We did that work with the unit circle, and so hopefully we're getting better. We kind of know those values. We could draw the unit circle. We could put some of those on. We could use our hand, whatever. But now we got this thing with the triangles too. So now if we've memorized the 30-60 triangle, the 45-45 triangle, we can draw the circle, we can put in the triangle, we can put those numbers on. So we now have several different ways we could answer these kinds of questions, especially with the 30, the 45, the 60, right? When it gets into those. All right, now today we're going to talk about what about other angles, what about 57 degrees? What about, what are we going to do with those, right? Some of it's going to be calculator, some of it's going to be some other things you'll see here. But, so if we take maybe an easy one like 57, and I say easy, so sine theta equals 1. I'm just curious, somebody want to volunteer to explain how they thought about this and got the answer for this one? Because basically the question is, solve this equation. Basically you're saying solve this equation, right? It's kind of like the old get x by itself. We're kind of saying get theta by itself. Now you can't, it's always funny when it's funny, but sometimes on calculus, and students will say, well, what do you do to both sides? And they'll say divide by sine, right? I mean, get rid of theta, right? It looks like you're timing it. No, that's not what you're doing at all. It's a function, right? We're asking ourselves what theta would make the sine equal 1/2, right? That's what we're asking. So we're saying to solve it. Now later we will talk about what are you doing to get rid of that sine. It's called inverse sine, but it's not dividing, right? That's not what we're doing. So, but it's what theta makes that work. Somebody want to explain how they got that? Come on.
You did. So I thought pi 6 leads to 1/2 the y.
From the unit circle?
Yeah.
Were you thinking the unit circle?
Yeah.
Right? If you're thinking of, I agree. I think that's one way to do it. If you feel pretty good about the unit circle, and right over here, I'll be honest, that remember we were talking about favorite trig function, or favorite trig function is sine, right? What always made sense to me in memorizing the unit circle is I always remembered, I just memorized this. I just always memorize this. Sine of pi 6 equals 1/2. Sine of pi 6 equals 1/2. Because I felt like if I memorized that, sine of pi 6 is 1/2, then I know cosine of pi 6 is the other one that goes with it, which is square root of 3/2. And I always knew the square root of 2/2 one was easy. That was pi 4. So I guess I memorized that one too. But so I always remembered. So how do I keep track of square root of 3/2 and 1/2? Those always seem to be confusing. So I just memorized this. Sine of pi 6 equals 1/2. Sine of pi 6 equals 1/2. I used to say it to myself before I went to bed every night. Sine of pi 6 equals 1/2. Sine of pi 6 equals 1/2. Sine of pi 6. So now I knew if it was sine of pi thirds, I'm like, oh yeah, that's square root of 3/2 because I know sine of pi 6 is 1/2, right? And so I remember that, and then once I knew that, then all the ones in the other quadrants you could get, and so forth, so on. Okay, so everybody's got their own little trick. Whatever makes sense to you to do that. So I kind of hear Caleb saying that, so sine, and you said the y, I like that too. So you know theta is going to be pi 6 just because of the work we did with the unit circle, right? I got it. Okay, and then what else? But there's 2 answers, it says. Right?
Yeah. Well, the other one's like for part B.
No.
Oh, are you talking about the degrees?
No. Actually, okay, so this is good. It says find the values of theta in degrees, 0. Oh, no, time out. You're right. Okay, never mind. I'm thinking about different. It says find the values of theta in degrees and radians. So it says theta 0 to 90, theta 0 to pi half, right? So the other one is degrees, so that is 30 degrees, right? Okay, good enough. We'll stop right there. So that's all they wanted. Now, so here's did anybody do triangles? Did anybody think of triangles here? Okay, so I think that's another way to do it, right? I think that's another way to do it. Now, what triangle did you think of, or Claire, how did you think of the triangle?
Like the 30, 60, 90 triangle.
Right.
1/2 is like opposite of the 30.
Okay, and so 1/2, so you think of the triangles, right? I agree. And so anytime we see 1/2, square root of 3 over 2, square root of 2 over 2, right? You could think of the triangles. Now, you could also think of the unit circle, but you can think of the triangles. And they're both equally okay, right? It's kind of whichever one works for you in that scenario. So right away, when we see this, I put in my 1/2. I know 30's here. I know this is sine, so that's SOHCAHTOA, right? You're thinking that. So opposite over hypotenuse. Oh, it's got to be the 30 degrees. That would be the sum. If this was cosine, then it would have been cosine equals 1/2. Then I'd have had a 60 here, right? Or a 60, so adjacent over hypotenuse, whatever. So that's a good way to do it too. So there's your 30 degrees, there's your 5 or 6. Okay, so I guess what I wanted to say about that was you could do it with triangles. You could think of it with the unit circle, right, and get it in degrees. Both equally okay. Now, sometimes when you get to one like 61, where it's like 2 root 3 over 3, it's kind of in a weird format, so you might have to play with that a little bit to get that one. But, okay, so fine. So we're going to go on. So 64. Right? Was that the first one I heard then? 64. All right. So we've got this triangle here, because our emphasis right now is in degrees in this section. It is on triangles, but that doesn't mean we forget about unit circle. That certainly is valid. All right. So 64 says solve for x. So you got x down here. You got 30 degrees here. You got 30 here. So this pretty much goes for all of and this is pretty much what you did in geometry, I think, and this is pretty much what we do on our story problems is we want to get our picture here, and this is opposite over adjacent, so which trig function is being used? Tangent. So, and then this is, was this, yeah, just x, so we'll just find x. So it's going to be tangent of 30 degrees is equal to 30 over x. So maybe the question is solving that. Is that the question maybe? Okay. Now you can think of it a couple different ways. You can always put a 1 under here and do cross multiply. Okay. Or move the x over to this side. It ends up being the same thing. Move the x over to this side, which would make that x times tangent 30 degrees equals 30. And then divide by tangent 30. So x equals 30 divided by tangent 30. Okay. Now, somebody else might be saying, well, why don't you just substitute right here, right? What is tangent 30? It's not 1/2. Tangent of 30, that's where we have to do sine over cosine kind of thing, right? So now, you weren't supposed to use your calculator here. Okay, really? I mean, this book does a pretty good job of putting kind of a calculator symbol or in the directions saying if they want you to use a calculator. So tangent of 30 would be sine of 30, which is 1/2, over cosine of 30, which is root 3 over 2, which goes back to knowing those values, right? Now, if you had to, you could think of you could do a 30-degree triangle, 1/2, square root of 3 over 2, and 1, right? You can always go back to that. right? So tangent of 30 would be 1/2 over square root of 3 over 2, which, how did that simplify? 1 over root 3, which is root 3 over 3. And at this point, I don't really care which one of those you use here. So I could have plugged that right there, right now, or I could just wait until here. It doesn't really matter. It's going to come out the same. So I got 30 over, and then what did we just say tangent 30 is that? So root 3 over 3, right? And I could invert that and multiply, so that'd be 30 times 3 over root 3, right? As it turns out, it probably would have been better to leave it like that, okay? On this, on the quiz, I'm probably going to be fairly lenient on that, but what you would do here is root 3, so that'd be 90 root 3 over 3. That cancels. That's a long ways to get the 30 root 3, okay? But that would, is that what the answer book had? Or that was 64? Was that it? Okay, so let me just look real quick here. 64, yeah, 30 root 3. Okay, so I think we want to leave it in that. Now, again, if I just would have used this, if I'd have done 30 divided by 1 over root 3, then I could have just inverted multiply. I'd have got 30 root 3 right away, right? Or I could have plugged it in here. I could have said, okay, what's tangent 30? And I could have found tangent 30 is root 3 over 3. And then had 30 over x like this. Okay? I could have just put the root 3 over 3 in for tangent 30 right now. And then I could have just cross multiplied. So now I get x times root 3 equals 90. Divide by root 3, I get 90 over root 3, which is the same thing I had here, and then I can simplify. Make sense? So either way, we got to do the SOHCAHTOA setup, and then, right, if it's a 30, a 60, a 45, we just know it without a calculator. We got to be able to do it, right? 30, 60, 45, automatically we just do it with our triangles, whatever, no calculator involved. I don't know on the quiz yet, it might be a part no calculator, part calculator, right, kind of thing. Or I might just say, hey, you got to put your answers, in this form. There are certain calculators, if we do something like that, I wouldn't let you use. I mean, that graphing one is still okay because it doesn't. But there are some, I don't see that anybody has one of those, but if you have one of those where you would type in sine of 60 degrees and it would say root 3 over 2, I wouldn't be crazy about you using that. But I wouldn't let you use that. But again, it's not that big a deal because if you get a decimal, if you just memorize 0.866 as root 3 over 2, you can still do it. So we might do a no calculator situation just so, I just think it's important that we know those values. But I'll let you know more on that. But so right now, do as much as you can without the calculator. All right. What else? 67 or 70? What was 71 for sure? 67, did somebody ask about 67? 67 also, okay. So let's just talk about these story problems. And again, they're going to typically be right angles. You got the Empire State Building, is it? Whatever it says. The angle of elevation. So here you stand, and you are 45 meters away from the base, and your angle of elevation, that just means the angle looking up. The angle looking up is 82 degrees. And that takes you to the 86th floor. Now, up above that is some more of the building. It's another 123 meters up, but we just care about this triangle. So basically what we need is that value right there. So this is very much like the last problem. It's opposite over adjacent. So we need tangent of 82 degrees, okay, equals x over 45. Well, here's where you get to use your calculator, right, on this one, okay? So, because it's not 30 or 45 or 60, right, and so we need it. So you would just type in tangent of 82 and times by 45, right? So go ahead and do that. Tangent 82 times by 45, that's going to give you x. And what was that? Anybody got it? I mean, if you didn't understand that, just go ahead and do it right now. But if you already had it, tell me what you got. 3,192. And then we would add on the 123. So that's before you add on the 123. Okay, and then you would add on the 123. That is the height of the building. One of your friends is on the 86th floor. What's the distance between you and them? Well, that would be this distance, the hypotenuse, right? Or R, we've been calling it R our triangles on our circle. So now you would just take this squared plus that squared, right? And then the square root of that. And what was that answer? 4 something? No, 3 something? 323.34. And that was what, 67? Yeah. 323.3, they rounded to that. And then height of the building was like 443 something. Okay, so there you go. That's 67. All right, 70, 71. Both. 70. How many want to see 70? Raise your hand if you want to see 70. Okay. 70. Width of a river. Bob just wants to know the width of the river so the instruments for studying the pollutants can be set properly. From point A, the biologist walks downstream 100 feet, sights to point C. From this sighting, it's determined 54 degrees. So here's the river across. We need to know that distance across. He walked 100 feet down the bank. This is the river right here. Da, 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 da. Looks like a river. And he saw that that was 54 degrees right there. Right? I got that right? So how far is it across the river? So isn't that the same thing? Tangent of 54 degrees. Whoops. 54 degrees is opposite over adjacent, x over 100. Okay, so we're going to just type in our calculator, tangent of 54 degrees times by 100, and we will get our x value. Tangent of 54 degrees times by 100, and that is 137.6 something. 137.6 feet. Okay, 71. A guy wire runs from the ground to a cell tower. The wire is attached to the cell. Now, one of the things we want to understand is when it comes to possibly our next quiz, problem like these, you may not get a picture, right? They gave you the picture on this one. They gave you the picture on the river. So be able to read it and be able to draw a picture. Okay, so some of you did not have a picture, some of your pictures drawn. I think that's important. Okay, so a guy wire runs from the ground to a cell tower. So you got the cell tower here. Guy wire, I'm going to purposely draw it different than they have because I'm just going to pretend that picture's not there. The wire is attached to the cell tower 150 feet above the ground. So the tower might be going up higher than that, but here's the ground, and it's attached, the guy wire is attached to 150 feet. Here comes a guy wire down to the ground. Okay? The angle formed between the wire and the ground is 43 degrees. So this is 43 degrees. Okay, how long is the guy wire? So you just got to know which one are we talking about. So that's that right there. So call it X. It doesn't matter what you call it. Call it R, call it C, whatever. You know, a lot of times X's are horizontal. I used X up there. It doesn't matter. We're not on an XY axis right now, so it doesn't matter. Okay, so which trig function am I going to use for part A? Sine, opposite over hypotenuse. So sine of 43 degrees is 150 over x. So whenever the x is at the bottom, it's kind of a weird one. But really, I think maybe the cross multiply. Does that make the most sense? I think cross multiply. What do you do when you cross multiply? Don't you do this times this and then divide by the other one? Right? So I think cross multiply might be the best way to think of these. Just put a 1 under that and now cross multiply. So 150 times 1 and divide by sine 43. And you can just do that right on your calculator in one step. Instead of multiply the x over, then divide, right? And, you know, it takes more steps. So maybe just put a 1 under there. Cross multiply might be the best way. Okay, so 1 times 150 divided by sine 43, and we get 219 something. Okay, and then how far from the base of the tower is the guy wire anchored to the ground? Well, that's that distance right there. Okay, now you got an option. Now I would say one of the things I tell the students in calculus, and you would learn this in science class too. So we've now found this distance, right? We could do Pythagorean theorem, couldn't we? Now, right? We got this squared plus y squared equals that squared. And we now know that, right? So we could find y that way. What would be the downside of doing that? Your answer for x is rounded. And I'm grading the bike problems, and there's a number of you probably talking together, I'm guessing maybe, which is fine. we're off by quite a few number of petals because you rounded a value earlier in the problem, and then that made it be off later. Now, I didn't take off very much. 1 point, I think, out of the whole thing. It's like 20 points or something. So I didn't take off very much because that affected several of the answers. Okay? And so whenever, and so in science class they would tell you this, so if you take a rounded value and then use it in further calculations, then that introduces more and more error into your final answer. Okay? So it's not a bad idea to just do another trig function. What trig function would use these two? Tangent. So maybe a good habit to get into when you're doing this, instead of doing Pythagorean theorem, once you find one of those sides, is to just go ahead and set up another trig function, because then that'll be a better answer, especially if we want to be to the nearest 2 decimal places or something. Using a rounded value could get you in trouble. Or worse yet, what if you screwed this up, right? What if you got this wrong here? You know, punched the wrong button or something. Now you're using a wrong value, and then that's going to throw off that next answer. So it might be a good idea to do that. So anyway, on this one, we would just take 1 times 150 divided by tangent 43, and I got 160.9 something. Okay, so that's something to think about there. All right. So let's move along here. If you want to get your notes out, or well, actually, write on your homework page if you want to do this. Let's do. Geez, boy, time goes fast in here. You guys are gonna so. All right, 79 right here. Read that question. Mars rotates on its axis at the rate of 0.2552 radians per hour. Yay, linear and angular velocity. Approximately how many hours are in a Martian day? Okay, rotates. Remember, a day is how long it takes to rotate one time around, okay? So how many hours are in a Martian day? See if you can calculate that real quick. It's not a long calculation. Now, what do you got? 24.62 hours. Pretty close to ours, 24.62 hours. Put that into hours and minutes. In other words, 24 hours and how many minutes? How many minutes? About 37, 37.2. What do? You just subtract off the 24, right? And so it's 24.62 something. So you just take the 0.62 something times what? 60, right? It's a fraction of an hour, 0.62, a little more than half an hour, right? And so 37 makes sense, but you just multiply that by 60, right? So take off the 24.62, and then just times that by 60, and that gives you the fraction. Okay, here's what I did. I wanted to show you this as an example of where, now, you may have just thought it through, and again, we've talked about this, you don't have to do it the way I did it here, but what I was thinking was I want to end up with hours. I want to end up with hours, so I wanted hours on the top of my thing, right? And I knew that it went 0.2552 radians per hour. Well, normally radians would be on top, hours would be on the bottom. I didn't want hours on the bottom. I wanted hours on the top. That's what I wanted to end up with. Okay, so I put 1 hour over 0.255 radians. So I wrote it as hours per radian. Okay, but I knew I wanted hours on top. Now I know I want radians to cancel, so 2 pi radians is 1 revolution, because what I wanted was how many hours for 1 revolution. So I knew I wanted hours per revolution, right? Hours for 1 revolution. And so that's how I set it up. But again, you may have just said, hey, it's 2 pi for one time around. And so we're going to take 2 pi divided by that, and you may have just done it that way. Okay, read number 80 here. Read number 80 real quick. So, part A. So it's going to go 1 time around, right, is radians in 365 days. So if you divide that, you'll get radians per day. And that's what we want. We want to know how many radians. We want to know what the angle is in 1 day. So we want to know radians per day. We want to know radians in 1 day. So 2 pi divided by 365, whenever that comes out as a decimal point. Oh, well, it's pretty small, right? I mean, it's a pretty small number. All right? So it's not going very far in 1 day. And so that would be that. Now, you would then divide. Now, I went ahead and kind of started over, but you said divide by 24, right? And so that's how many radians in 1 hour. So basically, this answers how many radians per day. The angular velocity is how many radians per hour. So that just means divide that by 24. So that's even a smaller number, right? Because in 1 hour, the Earth isn't going to move very much at all, right? So that's an even smaller number. And then this equation, V equals R times W. The linear velocity, remember, was the radius times the angular velocity, which is the radians per hour that we just found. So whatever this number is here times that. Remember, that was radians per hour. We multiply that by miles, what happens to the radians? Take radians per hour and multiply by miles, what happens to radians? Just kind of goes away. Remember, radians is kind of that unitless thing that when it runs up against another unit, just disappears. So that's how come you end up with miles per hour. You have radians per hour, this answer, times miles, that gives you miles per hour. The radians just kind of go away. But it's this equation, okay? So radians per hour times miles. All right? And what does that number come out to be? I didn't. 66,705 miles per hour. It's a lot of miles. That's pretty fast, isn't it? You think about that, how fast the Earth's going. As it's going around the sun, it's going 66,000 miles per hour. So as we stand here on the Earth, we're moving right along. All right. So, get your notes out. So, now, I'm going to throw some terms out at you here, and we're going to, do some examples, go through a variety of examples. It'll carry over into the other side of lunch, and then you'll have some homework problems, obviously, again, to work on that, to try that. But then tomorrow will be a lot of review. We got an activity where they'll review this concept that we're doing. Really nothing really new tomorrow. Okay, that'll be on Monday's quiz. So tomorrow will be a lot about reviewing what we're about to talk about here, and then just putting it all together. The things will be on this quiz on Monday, and then on Monday we will review a little bit before we take the quiz. So Okay? So what we want to do in this section is take the two things we've been talking about, the unit circle and the triangle idea, and kind of put that together. Okay? So the unit circle is a circle of radius 1. We talk about an angle in standard position with its terminal side and all that. Now we want to talk about any size of circle. Matter of fact, you're going to notice I'm not even going to draw the circle. So we're kind of taking the idea of the triangles and putting it onto the XY axis, okay? The unit circles when you have a radius 1. Notice I've got an R on that triangle. We don't have to have a radius 1, right, to do trig functions. It's SOHCAHTOA. Why did we do radius 1? It just made it easier. It just made it easier. Since all the different size circles came out with the same size trig value anyway, we just made radius 1 because then opposite over hypotenuse was just y over 1. And so that's why we could say sine is the y and cosine is the x, right? Now it's still true. Sine is still the y and cosine is still the x because here's what we're going to do. We're going to move into these other quadrants. Now, we've already been in those quadrants. We've done it with the unit circle. So from that standpoint, it's not new. Okay? And when we're talking about the cosine, like the x being negative when you get over here, it's still going to be true. The x is still going to be negative when we get over here. The y is still positive when we get over here. R is always going to be positive. So what we're going to be doing is drawing some triangles in these other quadrants. Okay, trying to take our unit circle work and kind of put it into triangle notation, okay? And so for this purpose, understand R will always be positive. The radius R will always be positive. But X and Y can still be positive or negative depending what quadrant we're in, okay? So we can still think of the sine as the Y and the cosine as the X, okay? All right, so notice I got the three trig functions here. We've written that before. It's opposite over hypotenuse, x over r, y over x, right? So we still get that part of it. And of course, Pythagorean theorem, x squared plus y squared would equal r squared, right? All right, so this is just quadrant 1. It's easy. It looks like just all the other stuff we've done. All right, but what happens when we move to the other quadrants, right? So here's what it will look like. So if we do an angle in quadrant 2, we know we start on the x-axis, we go counterclockwise, our terminal side is in quadrant 2. We could draw a triangle. Now notice the triangle I drew. We always draw the triangle to the x-axis. We always draw the triangle to the x-axis. So here's a point on this terminal side. And we always draw down or up. We never draw a cross over here to the left. We would never draw a cross like this. We always draw our triangle to the x-axis. Okay? Now, in this scenario, the x is going to be negative. Now, it doesn't make sense in geometry class to call the side of a triangle negative, right? We would never do that. We would always be, in those story problems like today, everything would be positive. It would all be quadrant 1 kind of stuff, okay? But when we put it onto the quadrants, now this is negative, and of course the y is positive. And there's r here. I didn't even write an r there, but there'd be an r on it, okay? Well, in this quadrant, the x is going to be negative. The y is going to be positive. In this quadrant, they'll both be negative. X and y will both be negative. And in this quadrant, the x is positive and the y is negative. Right? So again, what are we going to do? We're going to think x is the cosine, y is the sine, right? Just like we learned with the unit circle. So when I say they're both negative, when I say x and y are both negative here, that means that cosine and sine are both negative, right? Now, what's tangent going to be down here? Isn't it going to be positive? Because what's tangent? Y over x. If they're both negative, tangent will be positive, right? So as long as we know what the x and y are, we know what sine is, we know what cosine is, and we know what tangent is, okay? And again, we know from the unit circle that all the first quadrant values are the same values we get in these quadrants. They'll just differ by a positive or negative sign, okay? Now, again, the difference here is, so what are we doing that's new? Well, what we're doing that's new is the unit circle was only good for us for those special angles. The unit circle was really only good for 30, 60, 45, right? What we want to be able to do is any angle. What about 57 degrees? That kind of thing. Okay, so this is where this comes in a little more. All right, so I went ahead and wrote this, and I don't think you need a new drawing. You could just write it on top of this if you're interested in putting this in your notes. But so in this quadrant, cosine, sine, and tangent are all positive, right? So what about in this side, this quadrant? What's cosine? Cosine is the x, so it's negative. What's sine? Positive. So what's tangent? Tangent is sine. We've already talked about this. Sine over cosine, or y over x. Either way, right? Think of it either way. Tangent is y over x, or it's sine over cosine. Okay? Those are interchangeable, because x is a cosine, y is a sine. Okay, so tangent would be negative there. What's cosine down here? Negative, because it's the x. What's sine? Negative, so like we just said, what's tangent? Positive, right? Tangent is positive. Okay, and then finally in the fourth quadrant, what's cosine? Positive. When we say what's cosine, we mean its value, not the angle, the value, right? Cosine would be positive. Sine, negative. What's tangent then? Tangent's got to be negative, right? It'd be sine divided by cosine, so it'd be negative divided by positive. Okay, so those are, and again, we kind of already knew this, and we especially knew it for sine and cosine when we did our unit circle. Now, when we did the unit circle, we didn't talk as much about tangent, but we did. I mean, we did find those. We just took the y coordinate divided by the x coordinate. That was tangent. That's where we got square root of 3 or 1 over square root of 3, those kind of things. Okay, all right. So this is kind of the new thing today. This is the new thing that we're talking about. That other stuff we just did is just kind of organizing some thoughts, but really nothing new with those values. Okay, so the new thing is this idea of a reference angle. All right? If theta is an angle in standard position, right, which means initial side on the x-axis, and then terminal side going counterclockwise like so, okay? So if theta is an angle in standard position, its reference angle is the acute angle, we'll call it theta prime. So you'll see that in your book, you'll see this theta prime. Its acute angle, its reference angle is the acute angle theta prime that's formed by the terminal side of theta and the x-axis. Okay? So let's draw a picture to go with that. So let's put one in the third, let's put theta in the third quadrant. All right. So if I put an angle down here, let's put it right down here. Okay? So there is theta right there. I don't like that. All right. So that is theta right there, all the way around. So somewhere between 180 and 270. Okay? The reference angle, theta prime, is going to be formed by the terminal side and the x-axis. In other words, right there. And this is what I was talking about a minute ago, where I said we're going to make our triangles always go up or down to the x-axis from our terminal side, never over here to the y-axis. That is always going to allow us to create an acute triangle where we can do SOHCAHTOA. So you can use this then, if you can memorize the points of the unit circle. If you can't, if you're not sure, you can always draw a triangle on the XY axis. And then if this is a 30 or a 45 or a 60, so let's say that was 150 degrees. No, it couldn't be 150 degrees. That'd be silly. Let's say that's 240 degrees. Let's say theta is 240 degrees. What would theta prime equal here? What would theta prime equal? What would the red theta be? Theta prime. Let's stay in degrees. If I give it to you in degrees, let's stay in degrees. 60 degrees. It's always going to be an acute angle, and that's going to be 60. So you see how if you didn't like memorizing that unit circle, you could take 240 degrees. Oh, that's 60. You know what? I know across from the 60 is root 3 over 2. What's across from the 30 here? 1/2. And then I don't care about this. I can make it a 1. Doesn't matter. But isn't this negative? And isn't this negative? And look what you got. You got the coordinates, you got your sine and your cosine, you can get your tangent, and away you go. So any angle you're given, we can draw what's called a reference angle. So 240 would have a 60-degree reference angle. So its values would be the same as a 60 degree in the first quadrant. We would just have to then put the signs on it for the quadrant we're in. And we just talked about how cosine and sine are both negative. Okay. Anybody?
Stop.
All right. So we were saying reference angle. So the reference angle is always an acute angle in the quadrant. We draw the terminal side, and again, we put a point on that, and we can draw a triangle to that angle, to that terminal side. It's always drawn to the x-axis, and it creates a triangle. And if it's a 30 or a 45 or a 60 type triangle, then we can just put our known numbers on it, and then just know what the cosine sine would be from that. Okay, but also, and what you'll see here is, but it could be some other angle than those, and then we would have to know some points on there. And so let's just take a look at what some problems would be like. So okay, so go ahead and draw this picture, and go ahead and draw your triangle in there, draw in the reference angle, okay, label it, and then find what sine, cosine, and tangent of 120 degrees would be. So the directions on a problem like this might be draw a triangle or draw an angle in standard position of 120 degrees, show the reference angle, find these 3 trig values, something like that. So it would talk about a reference angle. It would talk about drawing a triangle. Get too far into it just to make sure the triangle is there, right? Right? You know what I should have said? I should have said that the triangle is always drawn to the x-axis. I should have said that. My bad. Why did I think of it? But yeah, I mean, you put that in there.
I was looking at it, that was what I needed.
Sure, absolutely, absolutely. All right, so something like this. Right? And wouldn't the reference angle be 60? The angle in here would be 60. Now, how do you know that? Well, it's 180 all the way to here, right? So you go 120, how much is left? 60, right? 60. So 120 plus 60 would have to make 180. Okay, or 180 minus 120 if you want to think of it that way. Okay, but the reference angle, so we just draw down to here, make ourselves a triangle. Reference angle there is 60. So there will be some questions, I'm sure, on our next quiz is 120 degree angle, right? It's reference angle, radians and degrees, right? So 120, so it'd be 60 degrees, be pi thirds reference angle if we were doing radians. Okay, now, again, that should agree with our unit circle, right? 2 pi thirds, 120 degrees is 2 pi thirds. You look at 2 pi thirds, the x coordinate is negative 1/2. That's cosine. The y coordinate's √3/2. That's sine. And then tangent is sine over cosine. So this over this, negative √3. So it's no different than, answering them with our unit circle. All right, it should be no different. Just another way to think about it, depending on the problem. And for some of you, you may like this better than trying to remember those unit circle points, right? And just, but this is going to be more useful for us in what we're doing, 132 degrees, things like that. Things that aren't the special angles. This is where this is going to be of value. Okay, let's try that one. Okay, try that one. Now, as you're finishing that up, the negative 135, of course, the negative means we go in the negative direction. But as far as figuring the reference angle, you don't have to think about negative 135. You can just say, okay, that's 135 to there. How much more gets me to 180? 45, right? Or you could do coterminal. Remember where we added 360? Like you could say, well, add 360 onto that, it'd be 225. So it's 225 going this way. Well, that would be 180 plus what? That'd be 180 plus 45. Again, however you need to think about it to figure out that reference angle. So the reference angle is 45, which makes out a 45-45 triangle. Again, label this as negative because it goes left. This is negative because it goes down. we said in our earlier notes in quadrant 3, sine and cosine should both be negative. Remember we said the r, the radius, is always positive. So that 1 is always going to be positive all the time. So the sine is the y over the opposite over hypotenuse, cosine's adjacent over hypotenuse, and the tangent is opposite over adjacent, which would just be 1. And we said the tangent would be positive in that quadrant. Okay, and it is. All right, let's try one in radians. I think I got one here. Yeah, let's try that one. And then you guys actually draw the angle yourself. So that's 11 pi 6. 11 pi 6. Go ahead and draw that scenario. Now, reference angles is one of those scenarios where putting it into degrees might be helpful to you. So if you want to put it into degrees and then back to radians, remember though, if the problem's given in radians, we want to stay in radians with all the answers that we give and our work that we mostly show. So if you want to convert 11 pi 6 into degrees, you can, but if you want to look at something. So if you converted that, it's 330 degrees, okay? But if you don't, here's how you would think about it. Remember, we've talked about this. All the way around is 2 pi. That would be how many 6? 12 pi 6, right? All the way around is 12 pi 6. So 11 pi 6 is going to go pretty much all the way around, but it's going to be short how many? 1 pi 6. It's going to be short 1 pi 6 from 12 pi 6. So that's what our reference angle is, pi 6, which of course is 30. So in a 30, so this is a 30-60, and some of you I know were writing your angles in here too, so that helps you, know what's across what. That's fine. Crossing the 30 is always the 1/2, and it goes down, so it's negative. And then this is to the right, so that's positive, and then of course the 1 here. So sine is the y, cosine is the x, and tangent is the y over the x, sine over cosine, which is that. Okay? So values that we're used to seeing. So again, nothing different. We could have grabbed this thing. We could have looked at 11 pi 6 right there, and there's cosine root 3 over 2. There's sine negative 1/2. Same thing, right? Same thing. Okay. Don't even write this down, but so just grab your calculator and just think about it. See if you can just do it with your calculator and just visualizing in your head. Because I can just ask you this. Here's an angle. What's theta prime? What is the reference angle? I'll give you just 30 seconds here. What is it? I heard some 15s, heard some 75s, and that always happens. What is it? 75. Here's why you say 15. I know. So you go around, there's 270, you go 15 more. That's 285, but that's in here. We want the one that's here. So 285 would be down here. That's 15, so we got to do 90 minus 15 to give us the angle that would be in here, which is the 75. Instead of doing it with my air finger, maybe I should just draw. Okay. So that'd be 15 to there, but that's not what we want. We want that one. And that would be 75. But that's not an angle we know about, right? So we wouldn't know what those values are, but we can just do that. Okay. Last problem. Second to last problem. Third to last. Okay. All right. Here we go. I didn't know. I thought maybe this was the last problem. I knew it was coming up. All right. So, who planned this lesson? All right. So, here's the next scenario. So, 8, negative 6 is on the terminal side of angle theta. 8, negative 6. Okay? So we're going to pick up the pace here a little bit so you can start working. But remember, we're going to get a chance to go over this a lot more. And practice more. 8, negative 6, what quadrant are we in? Quick. We're in the 4th quadrant, aren't we? 8, negative 6 is down here. Boom.
Yeah.
All right, 8, negative 6, which means 8, negative 6, right? That's what that means when we have this point right here. Now, it's clearly not the unit circle because the hypotenuse is going to be way bigger than 1. So we would want to do the Pythagorean theorem here real quick. Go ahead and do it. 8, negative 6. Sometimes you're given the picture this way. Sometimes you're just given the point like that. But you would want to draw your triangle, put those numbers on. What's my number here? Give it to me in radical form. So do 8 squared plus 6 squared. Oh, is it it's exact? Oh, that's easy. Well, what would it be? In radical form. No, radical 100. Radical 100. See? So if I ask for it in radical form, just give it to me in radical form. Radical 100. Okay. Anyway, you're right. I forgot. Brain cramp there. Okay, it's 10. That's nice. If it doesn't, though, if it comes out square root 37 or something, let's don't put a decimal here. Let's put square root 37. Okay? Let's don't put that. You can use a calculator to get it, but let's leave it in that form. So you just do 8 squared plus this squared, and what that is would be square root of that. Anyway, now that we have that, these are all pretty easy, right? Make sure you put the positive there, the negative there. Remember, the radius is always positive. So sine is negative 6. Okay. Yeah, see, I knew. Why is it not just negative 6? Why is the sine not the y? Because this is not the unit circle, right? Remember, we said this earlier before lunch, sine in the unit circle is y because it's really y over r, but r is 1 in the unit circle. Remember, sine is opposite over hypotenuse. But when the hypotenuse is 1, sine is just the opposite, okay? But in this one, it's not. So it's negative 6 over 10. So we got to make sure we do that, and then we should reduce that. So sine is going to be negative 3/5. Cosine is 8 over 10, which is 4/5. Tangent is negative 6 over 8, opposite over adjacent, which is negative 3/4. And then these are all just the reciprocals. Right? So this is the thing. So we're moving away from the unit circle because we're going to deal with scenarios that are not 30, 45, or 60. And so we draw our triangle. We have those. We have the SOHCAHTOA relationships. Okay? All right. Given that, here's another way to say very much this same problem. Given that tangent is negative 7/3 and cosine is positive, find the other angles. Tangent is negative 7/3. So now we don't know where to draw the triangle. Here we knew because they gave us this point. But we kind of know here because what is tangent? negative, but tangent is SOHCAHTOA, opposite over adjacent. What triangle will the opposite leg be negative and the adjacent leg be positive? What quadrants? 4, or couldn't I write negative 7/3 as this? So couldn't the opposite leg be positive and the adjacent leg, or if you want to do y and x, that's fine with me. So don't we have to look at where y would be negative and x positive? That'd be down here. And y positive and x negative, wouldn't that be up here? But then they added this. Which one of these two is cosine positive? Cosine is the x, that's 4. So actually, when they threw on cosine's positive, we know the x is positive. That would throw out this possibility here, wouldn't it then? Because there the x is negative. So we know the x is positive, so it has to be in quadrant 4. So, and tangent is opposite over adjacent. So doesn't it have to be negative 7 and 3 like that? Correct? Now what's the hypotenuse? 3 squared plus 7 squared. Radical 58. Okay? Radical 58. And now away we go. Sine would be opposite over hypotenuse. We'll just leave it like that for right now. Cosine would be x over hypotenuse. We already have tangent. And then these are just flipped. These are just reciprocals. Right? Okay. So, we're given a point. We can draw our triangle easily with that point. We're given one of the trig functions. We just have to figure out, okay, what quadrant is that triangle in? So that fraction will be opposite over hypotenuse or opposite over adjacent or adjacent over hypotenuse, whatever. Okay? All right, finally, last thing. Yes, last thing. So, what about these angles? These are called the quadrant angles, sometimes called quadrantal, which is just a funny word. The quadrant angles. In other words, how do we do sine of 90? How do we do cosine of 0? Those wouldn't make triangles, right? You can't do the opposite leg from the 90-degree angle. That's the hypotenuse, right? Well, we actually already know this. Whenever we're doing quadrant angles, we're going to call this the unit axis. Okay? We know this is 1, 0, and by unit we mean 1. In other words, this is just the unit circle without the circle. Right? And we're going to do our old thing with cosine x, with cosine being the x and sine being the y. Right? That's how we're going to do quadrant angles. We're just going to think of the unit axis. So you tell me, what is the sine of pi halves? Pi halves is right there. What's the sine? It's the y. What's cosine of 0? Where's 0? Right here. 0 degrees is right here. What's the cosine? Cosine is the x. It's 1. What's tangent of pi? Pi is all the way around to there. What's tangent? Y over x. 0 over negative 1 is 0. What's cosine of 3 pi halves? 3 pi halves is around to there. Cosine is the x. 0. Sine of 2 pi. All the way around. Sine is the y. 0. Negative 3 pi halves. Oh, we got to go backwards. Negative 3 pi halves goes around that way. What's the tangent? Tangent is y over x. 1 over 0. Undefined. So the tangent, or excuse me, the quadrant angles are usually going to be 1 or negative 1 or 0 or undefined. And we'll just use those we'll just use those points, because we can't draw triangles. You can't draw a triangle at 90, right? Can't draw them. Okay, you can't go up to this point and draw a triangle down to here, just a lot. Can't do it. So you get any of these quadrant angles, we'll just use these points and do our XY thing with cosine and sine. Okay? All right. Intramural games tonight?
Mondays and Wednesdays.
Okay. Good.
I don't look like Ben with glasses.
Hey, I changed my mind.
I like that. I think.
I changed my mind. I need to add something. Just kidding.
Don't do
Don't do 1 through 6.
Are you sure that's the section you want?
That's the only section. No, not 27 through 97 odd, or no. 37 through 67 odd.
But how do I figure it out?
Yeah, it's not. It's a few. Yeah.
I swear, there's like an A and a B.
There is on some of those in there. I don't think there is here. Let me look. Hey, look at this though. 75 through 90, you just get a type in your calculator. You gotta make sure you're in radian mode or degree mode, okay? So those you only have to type in your calculator. Man, gosh, this is actually easier than I thought. Maybe I shouldn't take those away.
No.
Well, I probably will forget and do them anyways.
Oh, you'd already put your thing away?
Yeah.
Oh, well, that's your fault for packing up too early. That's what you get. Oh, yeah, this'll take you 10 minutes. Maybe a little more. But it won't be.
I'm gonna be gone tomorrow, so is there anything I can do?
No way you want.
Yes, I swear on everything.
Probably didn't know.
No, I don't have the worksheet right now.